Okay, good morning, everyone. I think this is 141, lecture 16. Okay, so Dan is somewhere in Oregon doing something we don't know. Uh, Today, I think, oh, good. Today we'll have, I guess we hopefully we can start dynamic logic, but we'll probably finish up past transistor logic. Dan told me that he didn't get to finish most of past transistor logic last time. So he also said that there's some administrative stuff. Well, he sent me the slide. So project help in labs this week. So uh, that's it. And then homework 7 will be posted on Thursday, and then projects due on Monday, 5 p.m. And then you're supposed to submit electronic reports, email that, and do not forget to include your SPICE file in your report. No slides, whatever that means. But I guess it's just a plain report. Okay. So any questions from? Well, I don't even know what you did last week, so that's cool. Oh, there it is. So last lecture you had past transistor logic. I guess you just finished up static CMOS. Okay, and then we're looking at alternatives to the static CMOS. Okay, so going to past transistor logic. Okay, so last time we talked about, I guess, this using transistors as switches. So we already knew that we can past transistors behave as switches, and then we're pretty much switching VDD and ground to the output. So why not switch some other value to the output instead of just VDD and ground? And then as you can see here, we can save a lot of area. You don't really have to create that P network. You just have to create an N network to implement your logic. Anyway, the P network, the pull-up network in static CMOS is redundant. Okay, it implements exactly the complement of the pull-down network. Now, if you have ideal switches, such as what you see in the graph or the slides, then you will have no static power dissipation. Okay, what does that mean? The switch itself will not consume any power when you have static conditions, when the inputs are not changing. Okay. So you also looked at an example of past transistor circuit, this AND gate. Now, if you look at this AND gate, what does it remind you of? Transistors. Now, it's basically what? A multiplexer, right? Every time you have something, you can select inputs, select from several inputs, and pass that to the output. Then you have a certain type of multiplexer. And how do you design for multiplexers? So, if you have, for example, a certain logic function, how would you design that logic function using multiplexers? So, let's look at this example for the AND gate. Okay. So, if I have an AND gate, where is that? Okay. You have the truth table for an AND gate. So if I have A, B, and the output F, so 0, 0, 0, 1, 1, 0, 1, 1. So what's the truth table? It should be 0, 0, 0, 1. Now, notice that I can always express a function. Okay, I can always express f as a function of another variable, of one of the input variables. Okay, and I think they call that variable entered mapping if you do that type of design. For example, if I have when a is 0, the output is pretty much 0. If a is 1, then if I compare f to b, then the output is just b. Okay? So it means that I can use a to select the function f, a and a bar. Okay, when a is 1, b should be routed to the output. When a is 0, 0 should be routed to the output. Okay, so that's usually how you design for multiplexer implementation. But this is easy. You can do this. So let's try a harder gate or more inputs. That's a nice. Let's do f equals, let's say a XOR b XOR c. 3 inputs. So what's the truth table for this? So you have 3 inputs a, b, and c. You have your output. Okay, hopefully this fits. So it's 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1. So a XOR b XOR c would just give you 0, 1, 1, 0, 1, 0, 0, 1. So which is what you'd expect, because this is approximately, if you have a full adder, this would be the sum function, right? So you want to reduce the number of input variables, transfer one variable to the input of your multiplexer. Okay, so if you notice that, you can break this up into this function. Okay, so for example, when a and b are both 0, the output will be equal to c. When a is 0, b equals 1, the output is just c bar. And then when a is 1, b is 0, the output is still c bar. And then when they're both 1, the output is c. Okay, so if you implement this using past transistors, then I have, obviously you have 2 switches in series to select 4 possible paths. Okay. And then you have a bar, b bar, a bar b, a b bar, and a b. And then obviously this goes c, c bar, c bar, c. And this gives you my past transistor implementation of my logic function. Any questions on this? So it's pretty straightforward, right? Well, if you have a larger number of inputs, I mean, you might not want to write out a truth table of 15 variables or something. So this is actually formally expressed as, I think it's called Shannon's expansion theorem, but you have to check. But in any case, it goes like this. If I have a function f of a, b, c, I can always expand this as f of 0, 0, c times a bar, b bar, plus f of 0, 1, c times a bar, b, plus f of 1, 0, c times a, b bar, plus f of 1, 1, c times a, b. Okay, so any logic function I can expand in terms of one variable. And this is basically what goes into your multiplexer, right? So if you have a multiplexer here, or let's just draw that in switches. Okay, so this would be f of 0, 0, c, f of 0, 1, c, f of 1, 0, c, f of 1, 1, c, and this would be a bar, b bar, a bar, b, a, b bar, a, b. This is my function of f of a, b, c. Okay. So you can do that for any number of variables you want, and then you can easily implement logic based on multiplexers. Okay. So we see that you can implement very, very complex structures with a minimum amount of transistors. And you can also do a lot of simplifications. For example, in this case, you notice that this is in... Oh, we can't do much simplification here. But if you have... You can actually simplify some of the branches. So for example, let's say... So I won't have to come up with another example. This is not C bar, but instead if this were C, okay. So for example, if this were C, not C bar, then I could minimize this branch here, these two branches, into just so both A bar and then B bar B then goes into C and so on. So you can combine branches if they have the same inputs and then the same control signals. So, but yeah, the thing is you can get very, very compact logic in this way. But basically nothing comes for free. So what are we paying if we implement logic in pass transistors? What's a characteristic of a NMOS being used as a switch? Exactly. When you lose a threshold voltage, if you have VDD here, if you have VDD here, then you always have VDD minus VT here, okay, to maintain the channel there. Now, if you look at the slides, can we switch here? Okay, good. We see that if this is not really that bad. Okay, the bad thing is that when it drives inverters or it drives static CMOS gates, what happens? Okay. As you can see in the slide, if it's driving this inverter here, okay, this inverter here, notice that when the input of the inverter is VDD minus VT, or in a normal inverter, okay, when the input is high, the NMOS should be strongly on, while the PMOS should be off, as strongly off as possible. But in this case, if the input is not going up all the way to VDD, what can we say about the PMOS? Can we really switch off that PMOS transistor? What's the requirement to switch off the PMOS transistor? The gate source voltage should be very much less than its threshold voltage. Okay. Now, if it's not, then we'll have what happens if the transistor is not fully off? Then you have current passing through it. And what happens to that current? Is that actually useful current that you can use to charge a capacitor or something? Not really. Why? Because when you want that PMOS off, all the work is being done by the NMOS transistor, pulling stuff down. Okay. So if we look at that, if you have if I have this, so I have VDD, and this would be VDD minus VT. Let's say VTN, obviously it's VDD. What's the gate source voltage of my PMOS transistor? VGSP, well, the absolute value is just VTN. Okay. Now, is this enough to turn on or turn off my PMOS? So notice that if you can make VTN the less than VTP, then you might be actually able to turn off your PMOS somewhat. But does this ever happen? Normally, if you look at your process, you would want VTN to be approximately equal to VTP. Okay. Now, if they're equal, we'll be able to turn off the transistor. Now, notice that here, the bulk here is normally connected to VDD, so the VT of the PMOS is just its VT0. Okay. What about for this transistor? Where's the bulk connected to? It's connected to ground, normally. So what's my source bulk voltage for this pass transistor? So where is the source here? This node or this node? It's normally the one with the lower potential. Okay, that's where your VGS is, right? That's why you have VT here. So my source bulk voltage is this voltage. Okay, it's VDD minus VTN. And what happens if I have some sort of source bulk voltage? Well, then my VTN would just be VT0 of the N plus, this. So it actually increases. Okay, so this would actually, in reality, this VTN would be greater than the threshold voltage of the P. So you really can't turn this off if you start out with a process with approximately the same threshold voltage. Okay, and what happens? Now I start to leak current here, while this transistor, the NMOS, for example, is discharging my load cap. Okay. Now, so one obvious consequence is that when this is high, then I actually have static power. When V in of the inverter is equal to VDD minus VTN. Okay. So that's a problem. So now what happens? So any questions on this? We get that we do have a problem. I mean, that's the important thing there. So what else? What happens to the delay? If I'm driving this inverter with something a little less than VDD, how will that affect this inverter's capability to discharge a load cap? It'll be faster, slower, the same. Slower. Why will it be slower? Actually, two things. So let's see. If I have this, and let's redraw that inverter. So I have VDD minus VTN. That's my output. Then I have. So for the NMOS, okay, the job of the NMOS is really to discharge this load cap. Okay, and you want to do that as fast as possible. So normally this would be VDD. Okay, if I look at my NMOS, probably I have this curve. If I had VGS equal to VDD, I have this much current available. But now I have just VDD minus VTN current available here to discharge the cap. But will all that discharge current appear or be able to discharge that cap? Will all this I appear or pass through the capacitor? No, because here I also have a leakage current from my PMOS. Okay, because it's not fully off. Okay, so if we look at my curve for my PMOS, Let's say ID, the PMOS, BDS. Okay, it's somewhere here. I have a VGS of around VTN. Okay, so this is for the PMOS. So everything is absolute value. So um, it looks the same. Okay, so I do have some sort of leaking into here. So what's the current left to be able to discharge this cap? Okay, this is constant. I mean, that's how the device is set up. I have a voltage VGS here and a certain voltage VDD, for example, here. I want to discharge that. I just have a certain amount of current. And here, this isn't fully discharged or fully off, so I do have a certain current here. So the current left for discharging this cap is just this current minus this current. So you actually get hit twice. Okay, you slow down because you have less overdrive for the NMOS, and then that has to sink the PMOS leakage current as well. Okay, so that makes this very slow. So what else? What else does using pass transistor have, or what are the other effects of using pass transistor on our inverter? What about the logic levels? What about VOL, for example? Let's look at this. What is VOH for this case? What's the VOH here? How low can the pass transistor pull this down? So if I put in 0 here, what happens here? 0. So if I have a 0 in the input of the inverter, what's the output? VDD. So my VOH is VDD. What about my VOL? Will my VOL change? So what'll be my VOL? So if you look at the curves here, okay, this leakage current is a function of the gate overdrive here. Okay, so I get this, and you want to pull this down as low as possible. It means that the VDS of my PMOS would be very close. If this is VDD, it'll be very close here. You have the same currents, depending on channel length modulation or whatever. Okay, so it means that during static operation, when this is high, and after you discharge most of the charge, okay, the current passing through the capacitor will be 0. Okay, that's when you have static conditions. You have 0 current through your capacitors. This leakage current will be equal to the current passing through your NMOS. And if this leakage current, if I put it here, I leak, okay, it turns out that I would not go all the way to 0, but I have a certain amount of VOL. Okay, and depending on the model you use, you can compute this VOL. Okay, I can use short channel, I can use square law, whatever. But the idea is you can solve it exactly. If you know leakage current from the PMOS, you can get your output low voltage for the NMOS. Any questions on that? Questions? We're going too fast, slow, we can speed up. Good. Okay, so if you look at the slides, okay. So you can see if you have a pass transistor driving an inverter, then node X case, the one you see in red would not be able to make it all the way up to VDD, but it will be at VDD minus VTH. And notice that the output, the green curve, okay, would be somewhat delayed. And you have this, if you look at this small green bump here, it'll be sorry about that. Yeah, so that's it takes 2 seconds to silence a phone. Okay, now so turn off your cell phone thing. Okay, where are we? Okay, so in delay, you can see that you do have some sort of well, it's not really seen here. Okay, you have some sort of VOL, but it really depends on how much your PMOS is leaking. Okay, and that's here. I exaggerated the example, but okay. Now, how do we go about? I mean, sometimes we really want to use pass transistors because we really want to reduce the number of gates or number of transistors that you have. So it turns out that we only get this problem when we try to interface pass transistors with static CMOS. Okay, so I can have one big chunk of pass transistor logic, and then I really have to worry about how I can interface these reduced output voltages to static CMOS. So one way is maybe we can use that ever so important concept of feedback. I'm sure in 140 you're having so much fun with it. We can use that to restore the signal. For example, let's go back here. Did I do something there? Okay, good. If you have okay. In this case, what if I put some sort of level restoring device, okay, here, such that if this is in VDD, I put in VDD, okay, initially I would get VDD minus VT. And what happens? This should start to go down. Okay, because obviously VDD minus VTN would probably be greater than the threshold voltage of my NMOS transistor. So I'll pull this down, and what happens? Okay, I get to some value here, VDD minus VTP. Okay, so I actually get a threshold voltage across my PMOS. Okay, what happens? Because this, as soon as this goes below this, it turns on this PMOS transistor, and then it allows me to pull this up to VDD, because we know that the PMOS transistor can pull this node up to VDD. Okay, so it looks like all well and good, but actually it gives some more advantages, because if you have the gate capacitance of your transistor, of your inverter, and whatever load capacitance you have here, then initially, okay, all the current will be coming from your input, charging this. But as soon as this goes down below VDD minus VTP, this turns on, I now have extra charging current from that transistor there. So I'd expect that I get some sort of speed up because I have more current available here. So that's good. That's for when the input goes from 0 to VDD. Okay. But what happens when I want to turn the thing off? What happens when, for example, for second case, when I want to turn off that inverter? So I apply a 0 at the input. So let's here. So let me just draw it. Yeah, so it won't get too cluttered. Oh, that's better. Good. Now, what if I want to put in a 0? And initially this was charged to VDD. Will I be able to drive this thing down to 0? So, what are the conditions for me to drive this node to 0? I need to be able to take out all that charge away from that capacitor, Cx, let's say Cx. What else do I need to do? Notice that as soon as VDD goes down, I'm discharging this, what happens to the VDS of my PMOS? VDS goes up. Okay, and we know that if I have a 0 here, okay, which is if I have 1 here, I have a 0 here, this is on. Okay, as soon as I create a VDS, it's gonna pump in current. Okay, so I'm not just taking out current from Cx. I actually have to take out current coming from my restorer, level restorer, R. Okay. So what's the worst case that can happen to you? When this inverter or this pass transistor, okay, can only sink so much current, right? If I have a 0 here, then I have a certain amount of VGS across it. Okay. If I have a certain VGS, certain within length, I have a certain current. Okay, and that current is fixed. Okay. Now, what happens if that current, so what do we have here? We have this charges, so this voltage goes down, okay, and then as this voltage goes down, I have current here. Now, if this current, if this transistor can only supply a certain amount of current, it's possible that I could have a static stable point wherein this is at some voltage, this current is equal to this current, and you have no current passing through the capacitor, and this capacitor can actually get stuck to some Vx greater than the switching threshold of my inverter. Okay, can that happen? Yes, it can. Okay, why? If you have you can look at this as what? They're switches, right? So there are 2 resistors and a cap. It's VDD. Okay. What happens? It depends on now my R of R and R of this N. This could actually get stuck at some voltage, Vx, that won't be able to switch my inverter. Okay. So what does that mean? It means that I have to size these 2 inverters such that I can actually pull this down, to pull this down, to pull this up. Okay. So notice that I just need to get through VM to switch this inverter so that this 0 goes to a 1 and then turns this off. Okay. So if we go to the slides, so we have the advantage of having full swing. The restorer adds capacitance, okay, but also takes away pull down network current at X. Okay, And now it's a ratio problem. How do you ratio the MA and MR such that you can actually pull Vx down to below the threshold voltage, the switching threshold of your inverter. Okay. And if you see here, this illustrates the voltage at Vx, okay, with respect to different sizes of the restoring inverter. Okay. So you can see if you have a wide inverter, it's 1.75 the width of the restoring transistor, it's 1.75 the width. Then you see that the voltage cannot be pulled down to zero. It stabilizes at some intermediate value, and then as you slowly decrease the width of the restorer, then that voltage becomes lower until what happens here? This knee here. The knees here approximately occur at some sort of constant voltage. What happens here? Can you see the mouse moving back and forth? Good. So what happens here? Why this? This is pretty much an exponential decay, right? So that's we're discharging your caps. But what happens at this time? It hits VM. Okay, so if it hits VM, then your inverter switches. It turns off your restorer, and you can actually see faster discharge times here. And why is this approximately linear? This is approximately exponential, and why the change of shape here? What's happening here? I'm discharging my cap through a transistor. Okay, it's acting like a current source, which what transistors are. Okay, so approximately you have constant current discharging until you reach the exponential part again. You go into triode. Okay, so this pretty much sets a limit on the restorer size. You should be able to pull it down, and it actually becomes worse if you have several transistors in the stack. As we saw in our example earlier, can we switch to here? For that multiplexer, you could have 2 transistors driving this inverter, now with a level restorer. Okay, so if I putting a 0 here, then the current here, if this were the same size as this, then the current here would be less. Okay, it means that I have to make the restorer weaker. Okay, and as we see here, okay, if this were a 1, okay, this would probably be approximately a 1. Okay, but remember this is a PMOS, right? So it has approximately half driving strength as an NMOS. Okay, normally it really depends on the technology you're using. Some people say, okay, you can use 1/4 the driving strength, increase the length by 4, and so on. But you have to figure it out depending on your technology and depending on your models. You can write out the equations here, okay, and see how much more current you want here than here, or how much current is being supplied by the restorer, and you need to overcome that to get below VM. Okay. So any questions here? Questions? Okay. Now, the second solution is pretty much what's causing that degradation or swing is a threshold voltage. Can we actually fabricate devices with 0 threshold voltage? Yeah. Okay. You've seen there's some work going on about everywhere using 0 threshold devices and so on. Well, it looks kind of good, right? You can use pass transistors, but if your threshold voltage is 0, then you don't have any degradation at the output. You can still get full swing at the output. But what happens? So if you have zero threshold voltage, any variation in your input, for example, if I have this transistor here with a zero gate voltage input, then if I have a certain amount of noise or whatever, I can have a path going from here to here. Okay? Because this you want on and this you want off. But if VG is very close to the threshold voltage, then you would have leakage currents, and this would probably leak. Okay? And you don't want that. Now, one way, I think you've already seen something like this before, is I can use redundancy. Okay? So if I know that when it's passing a 1, okay, it degrades the 1, but it passes a good 0, then if I have the output and its complement, okay, I know at least one of those would be good. Okay, the 0 would be good, the 1 would be bad. Okay, so if I have redundancy, for example here, differential circuits, then if F is good, for example F is 0, then F bar would be not good. But at least I have a good output. And then if F is a 1, it's not rail to rail, then at least F bar would be a good 0. So, but we saw this. Let me draw that again. You have this two complementary pass transistor network. This is some function f, and this is its complement. Okay. Then I always get some sort of f and f bar. Okay. Now the thing with this is you can easily do level restoration here. Okay, because you already have the complement here. I can do this. This is connected to VDD as well. I can do this. So I can restore the levels. Now, will this have the problem of ratioing the sizes between the level restorers and the pass transistors? No, because this is a feedback circuit. If you redraw this, okay, so for example you have you can redraw this way. This is the output of F bar, and this is my output here, this is my output here. Okay, this is connected to here, this is connected to here. What does this look like? DC VSL. Okay, if you look at the impedance looking up, okay, if you solve this small signal, okay, what happens if this changes by a small amount? Okay, so if you have small changes here, you can approximately use small signal analysis, and those in 140 will see that this is actually a negative 1/GM impedance looking up because it has positive feedback. Okay, so small changes here will actually rail these two outputs. Okay, so that's one good use of using complementary things. You get that positive feedback effect. Okay. So any questions? Now, if you look at this, back to the slides, if you look at this, notice that I can implement AND, NAND, OR, NOR, XOR, XNOR in pretty much the same topology. Okay. So they actually made some sort of standard cell library out of pass transistors. Instead of having, I don't know, hundreds of cells, they have a library with just 4 cells made up of pass transistors. and they can synthesize uh, pretty much any logic. Okay. So one advantage is I can have very, very regular structures, and I just change the inputs. I can change the functionality of the uh, circuit. Okay. Any questions on this? Now, one other option to take away that degradation at the output is to use transmission gates. Okay. So basically, it's just we know that a PMOS can pass a good 1, an NMOS can pass a good 0. Then we can just combine the two and create a transmission gate. Okay, what does that mean? So notice that first you need complementary inputs at the control, so C and C bar, so that you can turn on both transistors at the same time. Okay, and notice that for a 1 at A, you always get or for a VDD at A, you get a VDD at B. For a 0 at A, you get a 0 at B. Okay, so it's bidirectional, just like any of the switches we have, but it has rail-to-rail switching. Okay, now it requires 2 transistors, and you also have 2 control signals, C and its complement. Okay, so again, we see a trade-off. You can pretty much create good switches, but you go back to the problem of doubling the number of transistors. Okay, so it's still there. Now, if you look at how does if you look at the resistance of the transmission gate, we see that as you go from the V out goes from 0 to VDD, or 0 to 1. Okay, what happens? We know that the NMOS cannot pass a good 1 because as soon as it reaches VDD minus VT, okay, it turns off. So you have Rn shooting up, but the PMOS resistance just goes into the linear region and supplies the required channel or the required path from the input to the output. Okay, so when you have 0 at the output, then both of them are in saturation, and then the NMOS turns off while the PMOS goes into its linear region. Okay, where am I? Now, if just quickly here, if I have so let's say this is at 0 VDD, VDD, and this is, let's say, going from 0 to VDD. Okay. Now just to make sure we understand where these two transistors are operating. Okay. Now what happens when if you look at the VDS of the NMOS ID, okay, the NMOS will always have a VDD here, but notice that the VGS here is large, so it will start from VDD. As this goes from 0 to VDD, then the gate drive of the NMOS goes down. Okay, while keeping, well, this is approximately 0, so you're in the edge of saturation, or you're always in saturation until, okay, this reaches VT. So you go from here to here to here, where so it goes from saturation and then turns off. While for the PMOS, okay, what happens? This is always a negative voltage. So you have VDD as my VGS. Okay. So VGS for the PMOS. Yeah. VGS PMOS. And then it goes saturation. Okay. As I increase, so if I increase VDD, then basically I'm decreasing the VDS of my PMOS. It goes from saturation, then goes down to linear. And notice that it'll be able to bring that VDS all the way down to 0. And like this, it will cut off, okay, with a certain VDS left over. So we go from saturation to cutoff, saturation to linear. And notice that in slides, one good thing about putting those two transistors in parallel is that the resistance, the total resistance you see, okay, is approximately a constant, okay, which makes it easier to predict the behavior of your circuit, right? The less nonlinearity, the simpler the equations we have. So, any questions? Now, so you can make a multiplexer out of pass transistors, and you have a sample layout. I'm sure you're familiar with layout. Yeah, so it just shows that, yeah, you can lay it out. So, anyway, so we can easily make, so one important building block for arithmetic circuits, as you'll see later on, is the XOR gate, okay, because we can make adders out of that. Now, we can use a transmission gate to create very, very compact XOR gates, okay, such as this. It has only 6 transistors, approximately half of that in static CMOS. And no, I'm not cross-eyed. There are 4 here, but you need an inverter for B bar. Okay. Right. So you have B bar. Now we see that we can still design this like we did earlier. If we go to we know that for an XOR, 0 0 0 1 1 0 1 1, yep, 0 1 1 0. Okay, so we see that when A is 0, this is just B, and this is just B bar. So we can implement that in the usual transmission gate thing. This is the symbol for the transmission gate. So if A is 0, means this is A bar, and this is A, I want to pass B to the output. And if it were if A is 1, so this is A bar, I will probably want to pass B bar to the output. Okay. Now, if I write everything out, I'll need an inverter here. Okay. Now, the interesting thing about inverters and transmission gates is that if I have an inverter, I can actually insert the transmission gate in between the two outputs. So this would be A bar, A is B. Well, this node X is the output here. Okay, so this and this will be pretty much equivalent, right? I'm turning off the output of the inverter when A is not on, A is 0. When A is 1, then I pass the inverted value of B. Okay. And if I do this, then, I mean, transistors in series, I can always swap them. I can do inverter inside. This is my B. This is my A bar, A. And notice that this node is 1 when A bar is equal to 0. And this node is 0 when A equals 1. So I can actually swap this B. I can swap this with A. I can swap this with A bar. So instead of this whole thing, I have the A bar, B. And this should be the same as the slides. So let's go to the slides. So of course, it's your choice if you use A, B bar, but the same thing. So you have in this case you're inverting the A and using B and B bar, and then you're passing A, okay, when B bar is 1. Okay. So basically, this is a simplification of the multiplexer that we did earlier. Okay, but you still need an inverter for B and B bar, or to get B bar. Okay. Any questions? Now, since we can design stuff here, and then we know that, okay, good, rail-to-rail swing, that's nice. We still need to know how it affects our delay. So here we have your, I guess, a lot of people's favorite task is to determine what's the delay through a series of pass transistors, or in this case, transmission gates. So notice that since the transmission gate, its resistance is pretty much constant, we can model it as just some equivalent resistance with the capacitance to ground. Okay, so if I have a chain of transmission gates, I can compute its delay. I can model it as some sort of RC network. Okay, and how do I know? How do I solve for the delay of this type of RC network? Ooh, silence. How do we solve that delay? You can use Elmore. Okay, and what does Elmore say? What's the delay through this path, the one in the middle? Elmore says that the delay here, if all the R's and C's are equal, it will be, the time constant would be RC times, it will be N squared plus N over 2, something like that. Okay, so the delay would be proportional to the number of stages squared. It's a quadratic function of the number of stages. Okay, so if I have 2 transmission gates in series, how is that, what's the speed of that compared to 4 transmission gates in series? Okay, one will be 2 squared and one will be 4 squared. So the number of transmission gates in series affects your delay significantly, quadratically. And how do we linearize that delay? How do we make that delay as close to linear as possible? Okay, what did we do for wires? We know for wires, the delay is proportional to what? The length squared. Okay, and how did we try to linearize a wire? We plugged in buffers. Okay, so we break everything into segments, and what happens? Instead of having quadratic dependencies, we now have linear dependencies on the whole chain. And then how does that work? Let's go back here and see. So if you have RC, let's say you have n stages, what's my time constant for this one? It's just a sum RC and n plus 1 over 2 times, yeah, no, this is already the sum. Okay, this is actually derived from sum of RC times k from 0 to n, right? So if you have RC, then R plus RC, and R plus R plus RC, so each of that will be the sum. So you have RC plus 2RC plus 3RC plus 4RC. That gives you this one. Okay. So obviously it's proportional to n squared. So the idea is if we try to break this up into segments, and then we drive each segment with an inverter or a buffer, then what will be their new delay? Okay. Let's say you still have n stages. Okay. But now let's say you have m stages per segment. Okay. So if I have one whole, this is my whole transmission gate chain, I can break it up into segments. So this has n stages, and this has m stages. Okay. So how many stages would I have? Or how many segments would I have? It'll be, how many of this do I need? If this is m and this is n. It's n over m. Okay. Right? So, and then how many buffers do I need? Obviously, if I have n over m segments, I need n over m minus 1 buffers in between each segment. So what's the delay of one segment? Same thing. It's, let's see. So the delay of one segment is m plus 1 over 2 times RC. And since this is not time constant, this delay, you have this ln of 2 thing there. Okay. But this is for one segment. If I sum all the segments, it'll be n over m plus the n over m minus 1 times my buffer delay. Just this. And this gives me my propagation delay here. Okay. And notice that what does this do? If I have m segments, so this just cancels out, I take away the quadratic dependence on n, but it gets down to the linear dependence on n. Okay, so I just need to break it up into several components. Any questions on this? So this is actually, yeah, as you can see here, this one depends on m, this one depends on 1 over m. So what happens if I have a larger number of M's, I have fewer buffers, but larger delay here. Okay. So if I have smaller number of M's, I have less segment delay, but more buffers. So it actually suggests that there is some optimal value of M here. And how do we get the optimal of a function? How do we get the optimal of a function? So sometimes they're not rhetorical questions. Okay. So we know that it's just taking the partial derivative of dp in terms with respect to m, and then equating that to 0. And what's the partial derivative of this with respect to m? I guess it's ln2 rc this is n over 2 plus, or this would be negative n over m squared t buff. Okay? And then actually n's drop out. You get m squared is equal to t buff over ln2 to rc. Okay? So m, just the square root of 2t buff ln2 rc. Okay? So you actually get some sort of optimal number of stages per segment. Okay, given that I have n. Actually, this is interesting. This does not even depend on n. Okay, it only depends on the delay of the buffer and the resistance and capacitance of my chain. Okay, so if you go, okay, there it is. If you go to the slides, then you see that. Okay, did I make a mistake? Okay, good. So this is the delay of the buffer chain here, and I guess, yeah. Well, I'm sure square root of 2 over ln2 should be around 1.7. Hopefully. Okay. So any questions on this one? So you see that if you have a certain amount of chain, I can always break up a quadratic chain, okay, be it a wire or pass transistors or transmission gates, and I can more or less linearize that by adding buffers. Okay. So any questions here? And then you have, basically you can create larger and larger structures using pass transistors. In this case, a transmission gate full adder. Okay. Now, you actually learn a lot about full adders later in the course when you get to arithmetic circuits. But just to illustrate how they got this, let's go back here. So when you have an adder, you have two functions. You have the sum and the carry. Okay, and you have three inputs. Well, okay. So this is the A, B, and C in. Okay, so this is your full adder. So how do you get the sum? What's the expression for the sum? There's A XOR B XOR C in. Okay. Now in this case, it might be actually easier to just compute A XOR B. We know how to compute XOR, and we call that P. So this would be equal to P XOR C